So, in the last lecture we have derived oblique shock relations, and we have seen that flow turns as it passes through an oblique shock, and the turning angle is related to the wave angle and the upstream Mach number, and we have derived the well known theta beta m relationship. Now, this theta beta m relationship is exact relation. However, we see that this exact relation is quite difficult to handle for further analysis, because in most real problem the flow turning angle theta will be known to us as well as the upstream Mach number, and the wave angle will be the usual unknown. And we have seen that the wave angle in terms of upstream Mach number and flow turning angle is given by an implicit equation, implicit trigonometrical equation, and it is not very useful to handle analytically. For that purpose, for our ease of use, we will try or look for a first order approximation of this relationship, and for that we will consider only weak oblique shock solutions. That is, we will consider that part of the shock where the solution is weak shock and the downstream Mach number remains supersonic. And what we will try is we will look for a first order approximation for weak oblique shock. That is, we will consider that the shock is weak and the flow turning angle is small. That is assumption small amount of turning, small amount of flow turning, or theta is small. Now, we have seen that for small theta, we have already seen that for small theta the shock strength as we have derived earlier, that this is equal to gamma plus 1 by 2 m 1 square tan beta into theta. See, when theta is small, the wave angle, if we look to the curve in m theta beta curve, so for when theta is small, beta is either close to mu either pi by 2 or mu. That is the flow. There are two solutions for small theta. One is very close to the normal shock, where the flow wave angle is very close to pi by 2, or very close to the Mach angle. Now, if weak shock solution is considered, considering weak shock solution only, considering weak shock solution, beta is close to mu and M2 is supersonic, that is the flow still remains supersonic. Then this then the approximation reduces to m1 square sin square beta minus 1 becomes close to gamma plus 1 by 2 m1 square, and tan beta is very close to since we have tan beta is very close to tan mu, which is of course 1 by root over m1 square minus 1. Then we have P 2 by P 1 equal to 1 plus from 2 gamma by gamma plus 1 m 1 square to gamma by gamma plus 1, and we substitute this relation here to give it gamma plus 1 by 2 m 1 gamma into m 1 square by root over m 1 square minus 1 into theta. So, this shows that for a weak shock, the pressure rise across the oblique shock is proportional to the flow turning angle. That is delta P by P 1 to gamma m 1 square by root over m 1 square minus 1 to theta, or delta P is proportional to theta. That is, the change in pressure across a weak oblique shock is proportional to the flow turning angle. Similarly, other flow quantities delta rho delta t are proportional to theta. However, we have earlier seen that the change in entropy across a weak shock is proportional to the third order of the shock strength, which we have seen in case of normal shock, and same applies for oblique shock also, and hence the change in entropy delta S is proportional to theta cube. And we can see that when the flow turning is very small, then the change in entropy is almost negligibly small. We will also now look to the difference between the flow turning angle beta and the Mach angle mu. We have already seen that for weak shock with small deflection, beta is close to mu. However, what is the difference between mu? Let us say where epsilon is quite small and is much smaller than mu. The Mach angle, then we have sin beta equal to sin mu plus epsilon, which is nearly equal to sin mu cos epsilon, and cos epsilon is taken as 1 plus sin epsilon cos mu. Sin epsilon is taken as epsilon and cos mu. These are what is used compatible to the first order approximation. And this makes sin mu is 1 by m 1 sin mu is 1 by m 1 and cos mu is or m 1 sin beta is approximately 1 plus epsilon root over m 1 square minus 1, and squaring we can write where epsilon square neglected, which are compatible to first order approximation, and this gives m1 square sin square beta minus 1 is approximately this quantity, and which we have already seen to be gamma plus 1 by 2 m1 square by root over m1 square minus 1 into theta, and hence this gives epsilon is gamma plus 1 by 4 So, see that for a deflection angle of theta, the difference between the wave angle beta and the Mach angle mu is of the order of theta. Similarly, to our first order of approximation, we can also see that the similarly we can see that the change in velocity across an oblique shock is given as or we have delta W by W1 is minus theta by root over so these are the relationship approximated for weak oblique shock for small flow turning angle. Now, we will discuss about the turning process or the supersonic compression using turning. We have seen that across a shock there is an increase in fluid pressure and density. That is, when a flow turns through a shock wave or oblique shock, its density and pressure rises or the flow is compressed. Then this can be used to compress a supersonic flow. That is, we can use a turn or a compressive turn to compress a supersonic flow, and this can easily be achieved just by providing an angle. That is, if we can deflect the supersonic flow by an angle theta, immediately the flow is compressed or the pressure is increased. Now, this turn turning through now. If we turn the flow by an angle theta, we can find out how much will be the pressure rise using the shock relation. Similarly, how much will be the density and temperature rise? All these can be found out by the shock or oblique shock relations, and also we can determine how much is the entropy rise across this oblique shock or compression due to turning. However, if this angle theta is divided into several small angles, that is, instead of providing one corner with theta, if we provide a number of corners with much smaller angle, so but the total angle being this theta, then the compression will occur through successive shocks, and each of these shocks will be weaker than the total shock that would have been there if the flow had turned once through an angle theta. Now, when we achieve this turn by a number of smaller corners, then the shock at each corner will divide the flow field near the wall into number of segments of uniform flow. However, away from the wall, the shocks will tend to interact, and the flow will be as if passing through a single shock. Let us say that if you would have one turn of theta with the shock angle being beta, in each case there will be a shock and in this case also, using the principle of limited upstream influence, we can construct this flow step by step. Coming to this first corner, knowing the angle delta theta and m1 here, m1 and p1 here, we can find out what will be the m Mach number here and what will be the pressure here. Knowing the knowing the Mach number here and the flow turning angle here, again we can find out what will be the wave angle beta, and we can get this part of the flow, and so on. We can proceed and get the complete streamline. Now, after passing through this fast shock, the Mach number will decrease. We will assume that the Mach number remain supersonic throughout. However, the Mach number here, that is downstream of the fast shock, will be smaller than the Mach number upstream of the fast shock. And since the Mach number ahead of the second shock is smaller than the Mach number ahead of the first shock, so if these two flow turning angles are same, then the wave angle here will be different or higher from this wave angle, and consequently these two shock will be convergent. As if, that is, little away from the solid wall, they will tend to merge or intersect. Now, for single shock, let us say for single shock case, assuming still that weak shock and flow deflection angle is small, that is theta is still small, the pressure rise across the shock is proportional to theta and the entropy rise is proportional to theta cube. For the multiple shock case, let us say that there are n turns, each of delta theta, such that n delta theta equal to theta. Then the let us say that the final pressure is P n minus P 1, that is again delta P is proportional to n into delta theta, that is or theta. That is once again the pressure rise is the same as you would have obtained by turning the flow with a single shock. However, the entropy rise in this case will be and this is clearly much smaller than this quantity. So, when you have multiple shock, but each shock or each turn is of much smaller angle, then our total entropy rise is also much smaller compared to the single shock turn. If we take the ratio, this is delta S for multiple shock or multiple turn shock by delta S of single shock, then we have let us take an example. Let us say that we turn the flow by a single shock through 10 degree, that is, we have only one deflection corner of 10 degree. And we achieve the same compression by providing 10 number of smaller turn each of 1 degree. What happened? The pressure rise in both the cases are same. However, when we compare the entropy rise, you see in the second case, that is when we are achieving the same amount of compression by 10 1 degree turn, my entropy rise is 100th, that is 100, a factor of 100 of the entropy rise that we would have obtained if it were only one 10 degree turn. That is, a compression by a single 10 degree turn will have 100 times more entropy rise than compression by 10 1 degree turn. However, in both cases near the wall, the pressure rise, density rise, velocity rise, velocity decrease, all will be of the same order. Now, if we continue this process of subdivision, we can make this delta theta to be infinitesimally small, and making n larger and larger, making n larger and larger, making n larger and larger, we have delta theta approaches 0. And what we achieve is basically a turn through a smooth curved wall. That is, n tending to infinity and delta theta tending to 0 is basically a turn smooth curved wall. And then the change in entropy tends to also 0, that is, compression is almost isentropic. Now, in this case, when these shocks are becoming vanishingly weak, that is when delta theta tends to 0, the shocks become vanishingly weak, and basically these shocks are then Mach lines, and then each segment of the uniform flow between two Mach line, then each segment of that uniform flow becomes narrow and narrow, and finally they coincide with the Mach line. That is, in that situation flow inclination and Mach number are constant on each Mach line. Thus, when we limit or when we approach to this smooth flow, the velocities and flow inclination are continuous. That is, the velocities and flow inclination is continuous. Flow continuous. However, the derivative of the flow parameters may still be discontinuous. Discontinuous derivatives. Now, the approximate expression that we have already derived for small flow deflection, they now become differential equation approximate relations for small theta becomes differential equation, and in particular that is delta W by W 1 It should be noted that even though we have not written a delta theta, the theta which is the turning angle is always represents a difference in direction. Consequently, this is always in the differential form or difference form, and for a smooth turn this relation can be written as now. Let us see this configuration for close to the wall. Where there is no sharp corner, but the wall is turning smoothly, and similarly let us say there will be very weak shock from each point, and those shocks are almost the Mach lines. However, because of the convergence of these Mach lines, since the Mach number is continuously changing and the change is decrease, so that mu is increasing and we can show some of these Mach lines or and we consider one or two streamlines close to the wall. Of course, the inviscid flow, the streamlines will be parallel to the wall. And let us say that the Mach number here is m 1 and the Mach number here is m 2. Of course, holds for both the streamlines. Now, you can see this change in from Mach number 1 to Mach number m 2 occurs over, let us say that this distance for this particular streamline. However, the same change occurs over this distance for this particular streamline, and since these Mach lines are convergent, this distance is considerably larger than this distance. That is, on this streamline the changes are occurring over a smaller distance. Consequently, the gradients of velocity, temperature and all other flow parameters on these particular streamlines are much higher than the on these streamlines. And at this point of intersection where all these Mach lines are meeting, it simply implies that this changes is occurring over almost a 0 distance and the gradient is infinitely high. Now, since this cannot occur that is where it cannot occur in the region where Mach lines converge and this very high gradient occurs, and actually what happens that the flow which was very nearly isentropic in this part will no longer remain isentropic in this part. The diffusive mechanism will come into action and this will be, that is, all these Mach lines will merge together to form a simple oblique shock. So, if with respect to an observer looking far away from this corner, it will appear to be a single shock with same strength that would have been there for if this turning were by a single shock through an angle theta. This convergence of these Mach lines in a supersonic stream is again a typical nonlinear effect, and a decreasing Mach number or increasing flow inclination, both of them tend to make these Mach lines steeper and this Mach line converges. However, for any of these streamlines can be replaced by a wall, and that is for these or these, and flow near the wall can be treated as isentropic. Now, again let us say that if we have made this wall, this is also a wall, and replace this streamline is also a wall. If we replace this streamline is also by wall, then between these two walls there will be an isentropic compression, and because the gradients will always remain smaller and the compression process will remain isentropic without having a single stronger shock. Now, we consider the case of expansion, that is expansion by turning. This is obvious that if we have a corner like this, that is for a concave corner, then the flow will turn and it will expand. In this case, turn by an oblique shock is not possible. Turn by oblique shock is not possible. That we can see that if we had a shock here, let us say if we had a shock here, then W1, and once again we could have resolved these in terms of now there will be no change in flow direction of this normal component, and this component V 1 will remain unaltered, and we will be seeing that now this of course cannot happen, because it simply implies that if we need to have, since W 2 must be parallel to this wall, so this cannot happen. Since W 2 must be parallel wall, and consequently this expansion cannot be achieved through an oblique shock or expansion shock are not possible. This relation of course, we have seen earlier also. Expansion shock are not possible. Expansion shocks are not possible. Because what happens that if you see this what happens is this. What happens is this, that is an expansion fan occurs here, if the front has an angle mu 1 and similarly this has an angle mu 2. So, that is, and as you have seen that through expansion fan the flow turns through each of these characteristics, but smoothly to become parallel to the downstream wall. This we have already seen that the characteristics flattens or widens, again the nonlinear mechanism that makes the compression wave steeper and steeper, it makes the expansion wave flatter, and these characteristics lines become divergent. Consequently, the process always remain isentropic since the gradients decreases. So, expansion even when achieved through a corner, supersonic expansion even when achieved through a corner or sharp corner is still isentropic. That is isentropic expansion, supersonic expansion by turning, supersonic expansion through turning is always isentropic. And you see that flow up to the corner is uniform at Mach number m 1, and consequently, the leading Mach wave is straight line at the Mach angle mu 1. Similarly, the flow downstream is again uniform at Mach number m 2, and the terminating Mach line is at an angle mu 2 with respect to the downstream wall, and this centered expansion wave, the centered expansion wave is called Prandtl-Meyer expansion. So, what we see here that in a supersonic flow we can achieve compression and expansion simply by turning it. A compressive turn or turn through a concave angle or flow around a concave turn is flow through a concave turn is usually an expansion turn, while flow through a convex corner is flow in a convex corner is a compressive turn. When there is a sharp corner, a sharp compressive corner, the flow turns by through a shock and is compressed. However, if the turn is made through a successive large number of smaller angles, the turning approaches almost isentropic nature, and in the limit of a smooth compressive turn, the compression is also isentropic. For expansive turn or flow through a concave turn is always isentropic. Even if the expansion corner is sharp, the turn still remains isentropic, as well as turn through a smooth wall, expansive turn through a smooth wall is also isentropic. So, what we see that expansive turn are always isentropic irrespective of whether the turning or corner is sharp or smooth. However, compressive turn can be non-isentropic or isentropic. When the turn is through a smooth wall, it is nearly isentropic turn, but here also one must remember that near the wall only the turning is isentropic, but as we move away from the wall because of the nonlinear steepening effect, the Mach lines are convergent, and little away from the wall these nearly isentropic Mach waves become a non-isentropic shock, and the turn little away from the wall is always through an oblique shock and non-isentropic. So,